what I have on the board is a small portion of the ionization energy graph. Okay, you can see that it starts here. It's actually not bad in terms of how it's drawn. There are some mistakes on it, but they're not major. Okay. So this is my question to you. As I go across a period, okay? Let's say I'm going across. This is 1, 2, 3, 4, 5, 6, 7, 8. Okay? So this is going to be, let's say this is lithium. No, let's say sodium. Let's go 3. Okay? So this is sodium. No, we'll start with lithium. That's okay. You know what? We'll do both. We'll do sodium and lithium, okay? We'll do periods 2 and 3. All right? All right? So we'll do, follow along with me, lithium, beryllium, boron. What's after boron?
Carbon.
Good. Carbon, nitrogen, oxygen, fluorine, and neon. And the third period, you should be getting used to this. So what's after phosphorus? Okay, good. Yes? Now remember, on the periodic table, these are not next to each other, correct? And that's going to be big. I have something to say about that, okay? But let's just use this for now. Yes? I'm just listing elements. I'm not doing anything else, all right? Is that okay? Okay. So you can easily see this. We're starting off here with what? What is this? This is actually hydrogen, right? Good. Hydrogen. And then you're going to go up here, and what's up here? Helium. And then you're going to come back down to lithium, right? So what are these? What are these elements here? The lowest. The lowest. These here. Those there are the what? Those are the alkali earth metals. That's right. They have the lowest. They have the lowest ionization energies. So on your graph, that's something that's important to denote. That gives you some perspective. Okay? Notice though that they're decreasing, right? On the periodic table, what is this? This is vertical, isn't it? So when you go down a column, down a group, yes, you're going to decrease the ionization energies are going to decrease. Yes? Yeah. Okay. And you can also see that up here, this is going to be helium, neon. This is helium, neon, argon, right? So you can see that those are also decreasing as you go down the column, right? Yes? Yes? Now, you can very easily see as I go across a period, the general trend, not law, but the general trend is as I go from left to right across a period, the general trend is that the ionization energy levels will increase or decrease? What is it? Okay, Andrew, you changed your mind.
I said decrease both times.
You said decrease both times. Okay, let's see what it says. Okay, this is what? This is lithium, right? So that's here, right? Okay, now as I go this way, as you go 3, 4, 5, etc., look what's happening. What's happening to the general trend? So here's lithium, right? I know. Read a graph much? I know. It looks obvious now, doesn't it? It's like almost silly. Yeah. So here's lithium, and here is neon. So obviously, the trend is that it's going to go up, right? So this is going to increase, right? It's going to increase as it goes from left to right. It's going to decrease as you go down. Is that all on the film? Am I filming that? Okay, okay, we'll bring up the board here a little bit. Okay, is that all coming up? Can you see everything?
Yes.
Yes? Can you see everything, Anna? Anna, you are my videographer. Okay, imported from America. All right, very good, excellent. All right, you see that? Can you see it all? Well, you see all this? Yes, okay. So, as I go down the column, as I go down from hydrogen, lithium, here's hydrogen up here, lithium down, right? I am decreasing the ionization energies, right? As I'm going across, I am going to be increasing. See, that has increased, that's a trend, increasing, right? See how this is increasing, right? Now, explain to me why they say, can I erase this? Do you see this, right? You see this? Okay, I'm going to erase it, okay? I want you to look at this though. Okay? I want you to look at this. See this little spike here? See that spike there? I want you to focus on that spike for just a minute. You see that spike? Okay. Now, I'm going to erase everything. All right? All right? Now, explain to me why they say that as you go from left to right across a period, it's a trend, not an absolute law that the ionization energy increases. Why do they say it a trend? Why do they say trend? Why do they say trend? Trend. TJ.
There's some exceptions to that.
Be careful when you say the word, be careful when you say the E word, and I don't mean elephant. Be careful when you say the E word in chemistry, exception. You can say apparent exception. You know when they say apparent exception, meaning it looks like an exception, but it really isn't because it has a specific explanation, right? Yeah. You see these? Shma shma, shma shma. You see that? Shma shma, shma shma, right? What we're going to look at, we're going to look as to why that happens. Okay? I'm going to look at a couple of things. Okay? I want to give you some background. I know that I'm a little random abstract, but I'm going to tie this all together. So stay with me and stay participating. You guys are doing a great job. Okay? All right, you ready? All right, here we go. Now, let's look at something, okay? Let's look at something. You all right? Excellent. So, let me draw the atoms as you go down a column. Hydrogen, lithium, sodium, potassium, rubidium, cesium, francium, right? That's 7 periods, right? Is that okay? All right, so make sure I'm coming up here, Anna, okay? So I'm going to say 1, 2, 3, 4, 5, 6, 7. That's going to be that's not going to work. Okay, let's do this again. Okay. What I'll do is I'm not going to number them. I'm just going to say the first one's the first period, second period. Is that okay? Is that okay? Okay. So, all right, so it's going to be, this is going to be, right? Hydrogen, lithium, right? Is that okay? You with me? Yes? right? I think I'm going to stop there. I'm running out of room. Okay? Is that all right? Can I stop at cesium? I think that's cesium, right?
Yeah.
Is it? Okay. Let me make one change, though, okay? What's an obvious thing? See, look at the nucleus of hydrogen. What's going to have the larger nucleus, hydrogen or cesium? Who's going to have a larger nucleus? Yeah, cesium, right? So let's do that. I mean, that's big. That's important. Okay, so that's little. Let's get rid of all these little guys, okay? And we'll make it increasingly bigger, okay? So this is like a speck. Okay, that's a little bit more than a speck. That's like it's shma. And then it gets shma. And then it gets and then it gets okay? So let's write the nuclear charge here. This is 1. What's this? 3. What's this? 11. What's this? 19. 37. What's this?
55.
What is it?
55.
All right, so look at those nuclear charges, right? Right? Okay, you all right with that? Are you okay with that? You sure? Okay? All right, now, let me draw the third period. Is that okay? The third period? Okay. So, I'm not going to draw I'm going to draw the nucleus in later, okay? Is that okay? Yeah. Augustina, you okay? You look very excited. Now, you know, you just had open heart surgery, so you can't get too excited, okay? All right, I don't want to have to call an ambulance, so don't look too excited, okay? So, you have, okay, this is going to be sodium. So we're going to put 8 of them in, right? Okay, so sodium's first, right? Okay. Right? Three shells, right? That's sodium. What's magnesium look like? That's sodium. I'm not drawing in any electrons or any nucleus. So what does magnesium look like? Same. Yeah, the same. There you go. I'll try to draw it exactly the same. And if it doesn't look the same, it's only because you have really bad eyes. These are going to be so incredibly perfect. Okay? What's that? Aluminum, right? What's next? What's next?
Silicon.
Silicon. What's next?
Phosphorus.
What's next?
Sulfur.
What's next?
Chlorine.
Right? All right, good. I just wanted to do that, okay? And what about this? Which one has the larger nucleus?
Argon.
So this is smallest? Okay, so this is like, jiba, and then jiba, and then nala, and then and then cha, and then bigger, and then ba, and then okay? Let's put the nuclear charge in here. Let's say this is going to be 11, 12, 13, 14, 15, 16, 17, 18, right? That's the nuclear charge. We'll say NC. NC. Nuclear charge. Okay, good. Now. Okay, now. I want to work with this first. Is that okay?
Yeah.
Okay, good. No, let's not do that. Let's work with this first. Okay. What happens to the ionization energies as I go down a column? Remember we saw that with group 1 and group 18, the alkali metals and the noble gases. Do you remember? What happens, Mike? What happens to the ionization energy as I go down a column? It decreases or increases. Yes? Yes, it decreases, right? And that's correct. But look at this nuclear charge. The nuclear charge is enormous compared to this is 55 times greater. That's a lot. The nuclear charge here is 55. Can I say that again? The nuclear charge here is 55 times greater, my shoulder is killing me, than hydrogen. Yet look at the size of that, but look at the size of the atom, right? But you would think that with such a great nuclear charge, that it would be hard to remove those electrons from the outer electrons. Are you having fun? I'm glad. But are you paying attention at the same time? Excellent. Thank you for playing. I appreciate that. Okay, now, so explain to me why the ionization energies would be less as I go down the column. Why the ionization energies would be less as I go down the column. Why the electrons would be more loosely held as I go down the column. Why the ionization energies would be less as I go down the column. Why the electron would be more loosely held as I go down the column. Why the valence electrons would have a decreasing ionization energy when I go down the column, yet the nuclear charge is 55 times greater in cesium relative to hydrogen. Why? 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 You ready? You want to tell you why? That's why.
North.
Earthquake.
Gravity.
The electrons are further from
What did you say? Gravity. Okay.
Gravity.
Clean up aisle 11. Okay. Sorry. Okay. Why? Watch. Okay? You ready? You ready? Your face is right here. Okay, you ready?
Oh, shielding.
Yes! Yes! Shielding effect. The shielding effect. Look at all of these shells, man. The shielding effect. You ready? The shielding effect. The shielding effect. The book is shielding, right? Look at all the pages, man. Look at this. What's better at shielding? This?
Yes.
Got it! All right, here you go. Shielding. Okay, you ready? Up!
Smash it, smash it.
So look at all of these shells here. Look at all these shells. The electron energy levels, the inner electron energy levels are saying, no, I am shielding the effect of the nuclear charge, which is 55 times greater than hydrogen. No. You will not pass.
You shall not pass.
What was that from?
Lord of the Rings.
Lord of the Rings. You shall not pass. Right? Is that good? Okay. So, do you see that? It's the shielding effect, right? So, let me ask you a question. As you go down the column, is the shielding effect constant, Andrew, or variable? It's variable. It's not constant, is it? Why? Because you have increased rings, don't you? You have increased size, don't you? Is that all coming up, Anna? Okay? Okay, special effects in Mr. Darcy's class. Okay, look at that, man. Look at that. Isn't that amazing? Okay, special effects. The board is doing it yourself. Ignore that man behind the curtain. Okay, you ready? You got it? Okay, good. Now, is the shielding effect here Constant or variable? Going from sodium to argon.
Constant.
It's constant. It's not varying. It's constant. It's not varying. Actually, let's just back this thing up. No. Yeah, we can back it up a little bit. Okay. Is that better? Okay, good. Yeah, I want to see both the vertical and the horizontal. Okay, so is that all on the board now? Is this one there? Almost? Is hydrogen there? Okay, and everything's here? Okay, so the shielding effect is constant, right? Right? And you know that the electrons are all being placed on the same ring, right? So, let's just talk, and I will make the connection, just so bear with me, okay? Now, talk to me about atomic radius, where the shielding effect is varying. So when I have a varying shielding effect, what do I have with the atomic radius? Do I have an increased atomic radius as I go down the column, or a decreased atomic radius? Increase, right? Because that shielding is preventing the outer electrons from being held more and more tightly as that nuclear charge is multiplying greatly. Yes? 55 times. Right? 55 times. But yet, the atom is growing very large. What is the atomic radius? I think it's page 180 or 280 or 480 or something. It's like an 80. What's the atomic radius of hydrogen? There you go, Anna. Perfect. Upper right.
0.037.
0. The atomic radius here is what?
0.037.
Is that right? Yes? Upper right. Right here. Yeah, it's 30. It's 30. It's 30. Where do you get 0.037? What is that number? I asked you for the atomic radius, not the ionization energy. Okay, but that's in a different, yes, that's fine. I apologize. But I apologize. I wanted you to look at the book, though. I wanted you to see in the book, not on the sheet. But I understand. Thank you. I didn't know what that number was. I was used to the one in the book. So what is it again, Anna, in the book? What is it?
30.
It's 30 here, right? And what is it for cesium? 55. What is it? 273. So it's a lot bigger, isn't it? Look at that. 30 versus 273, right? You get it? I'm almost there. I got 5 minutes and I'm going to do this. Okay? Now, what is the atomic radius for sodium?
191.
What is it?
191.
191. And just read them off. Now this is going to be magnesium. You're going to go across. Go ahead, Anna.
160. 143. 109. 109. 105. 102. 94.
So it's more than a trend, isn't it? The atomic radius is decreasing with a little blip in here, but it's pretty close, right? Right? You guys okay? Okay, good. You get it? Okay, now. So the valence electron that's being ionized, that's being removed, right? That site, where that is getting closer and closer to the nucleus, isn't it? So do you see why the ionization energy trend would be increasing as I go across the period? Because it's being more and more tightly held. Yes? There's no shielding influence, yet the nuclear charge is so powerful, the volume of the atom is collapsing in on itself. It's going from 191 down to 94. That's a significant drop in radius, wouldn't you say?
Yeah.
Now, but yet, where is there a drop in ionization energy? Instead of a steady increase, there's a drop. There's a drop right here, right? Where you get that dip. Michael, where's your ionization energy graph? Quickly, bring it up here. The big one. The big kahuna. All right, here it is. Look, here we go. You see this? Can you see this? I need give me a pencil. Thank you, pen. All right, here we go. You ready? Right, what am I doing here? Right here. Right here. Right here. See that? That's between 4 and 5. Do you see that? That's going to be 4 and 5, right? Because that's 3, and then 4, that's beryllium, and then that's going to be boron. And then there's another one here. Between what? What is that? What is that? What is it? What is it, guys? Come on. What's the first drop here? There's a drop here that we saw, right? Right there, and then there's another one right there. Right? Right? Here's neon, and then this is going to be fluorine, and this is going to be oxygen, and this is going to be what? Nitrogen, right? So between nitrogen and oxygen, right? Okay, so this is key. And then I'm finished. You ready? Okay. So here, between these two and between these two, right? These two columns. Yes? It happens between these two columns. So, but look at what happens. This is the first one. Okay. This is going to be beryllium. Right there. Should I put you with me?
Yeah, right.
That's beryllium, to remove that one, right? Yes? So you get an increase, right? Yes? And then look, you see a drop there. You see that?
Yeah.
It doesn't take much to remove that. That's why you have that apparent exception. Clear?
Yeah.
You get that? So this trend of a increasing ionization energy is based on nuclear charge and lack of shielding effect. What is the apparent exception a result of? What principle? It starts with an A. Sounds like AP, Aufbau principle. So the Aufbau principle says that, wait a second, this configuration is higher energy, this is lower energy, right? You get that? So in other words, it's the reverse. So if it's low energy, it's very stable. So it would take a lot of energy to remove that electron, right? So it would take more energy to remove that electron because that's more stable than that configuration. You see that? And the same is true here. You get this. Okay? You got to give me 2 more minutes. You're looking at that configuration, correct? For group what? Group what? 15 to 16, right? 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 Okay, so that's going to be 15, right? And then, so you're going to compare this one, removing that one, from a very stable state, half-filled P, and you're going to compare that one with that one from a less stable state. So again, those two exceptions are only apparent, they're not real exceptions because of the Aufbau principle will predict that. Now, this is key. Are you ready? This is key. Is the apparent exception between 4 and 5 beryllium and boron and between what's this? This is going to be magnesium and aluminum, 12 and 13, 4 and 5, or is it between group 2 and group 13? look at your graphs. If you have your graphs quickly, and then we're done. Take them out. Take out your graphs. Okay? Look at the ionization energy of calcium. Find calcium on your graph. Find calcium on your graph. Right now, quickly, number 20. Find calcium on your graph, number 20. Right? Now, according to the Aufbau principle, look at calcium and look at 31, gallium. All right? According to what we say, gallium should be going up, right? But gallium is below aluminum. So are you going to have that little reverse spike? With, in other words, is calcium should be lower than gallium because it's far away. It's over here, right? But where you have that exception between with magnesium and aluminum, you also have the exception between calcium and gallium. Do you?
Yeah.
Gallium is less than calcium. Do you agree? Calcium is 20 and gallium is 31. And according to the Aufbau principle, there should be an exception, apparent exception there as well, even though you have the entire 3D between the two. You get it? It's really important. Have a great weekend.
Naeem.
Don't forget shit.
He forgot the previous.
I'll take it.